Okay, so let's take a look now at how redox reactions, movement of electrons, can be used and can be harnessed and leveraged for some very important applications. And we'll take a look, first of all, at an example of a reaction that you would have actually done back in General Chemistry 1, where you had a solution, for example, of copper sulfate, copper 2 sulfate, which normally has that blue color associated with it. That's the solution here. And then we have a strip of zinc metal that's placed in that copper sulfate solution. What you would have observed and what you did observe when you did this reaction, even though it was on a much smaller scale, is that the color of the blue solution became lighter. So the color faded, the blue color faded over time. And then what also happens is around the zinc, you see these brown, sort of a brownish black solid that formed. Okay, and what's happening here is a redox reaction where the zinc solid, that metallic zinc that you see here, reacts with the copper ion that's from the copper sulfate. And as a result of this combination or this reaction that's occurring, the zinc actually becomes oxidized. So the zinc is oxidized. And as a result, the copper gets reduced. So the copper 2 plus gets reduced to copper metal. Okay, and that's the brownish black solid that you saw. As the copper gets reduced, well, what happens to the color? Well, the copper 2 plus, this here is responsible for that blue color. And as that copper 2 plus goes away, the color fades. That should make sense. As the copper metal is formed, it coats the zinc metal that's there. So what's happening, again, this is a redox reaction. If you look closely at this reaction, right, there is a transfer of electrons, right? Electrons are being transferred from something to something else. So the zinc here is actually losing electrons as it becomes oxidized to zinc 2 plus. And then what happens to the copper? Well, this is going to gain those electrons. It becomes reduced to the copper metal. This is happening in one reaction beaker in this case. And again, this is a redox reaction. So we have two half reactions occurring. We have the zinc solid becoming the zinc 2 plus ion. We have the copper ion becoming the copper metal. All right. So we have two reactions, two half reactions occurring. What we can actually do is we can separate these half reactions. And then what we can allow, we can force that those electrons to do is we can force the electrons to move through a wire, for example, an external wire. And as the electrons move through that wire, they will then generate electrical energy, right? So we're leveraging a simple chemical reaction. We're separating those half reactions from each other, and we're able to then convert that chemical potential into electrical energy, which is actually very interesting and useful if you think about it. So when we generate electricity through the spontaneous or through a spontaneous reaction, what we have just made is something down here that we called a galvanic cell. And a galvanic cell is just a setup for generating electricity through a spontaneous reaction. This galvanic cell is also referred to as a voltaic cell. So you'll see both of those terms used interchangeably. And all it's doing is we're using a spontaneous reaction, a reaction that would occur under normal circumstances without any input of energy. And we're able to then take that reaction and generate electricity from it. So we're now tying together chemical reactions to electrical energy. So what is happening when if we were to separate these two, right? So here we have now, in this case, we have a zinc in a zinc sulfate, for example, solution, ZnSO4, and we have a copper metal here in a copper sulfate solution, right? So those are our two half reactions that are occurring, or two two separate beakers. We combine them, we connect them, sorry, with a wire, and we allow the electrons to flow through that wire. So we have these two we've separated the oxidation and the reduction reactions from each other. And these containers that contain the reduction and the oxidation, we refer to these as half cells. Okay, so this is a half cell and that's a half cell. So we combine them together, connect them together, and we call that a galvanic or a voltaic cell. And again, we have those two half reactions occurring. So the oxidation reaction that's occurring is this one here. Okay, so we have our zinc solid becoming zinc 2 plus, AQ, and then we get our two electrons. So it's losing those two electrons. And then the reduction is happening in the reduction half cell over here, where the copper 2 plus ion is gaining those two electrons to produce now the copper metal. So each of these two half cells that we have a couple different components in it. So these metal rods that we put in here, these are called electrodes. So this is an electrode, and then this is an electrode. And by definition, the anode in a galvanic cell is the electrode at which oxidation occurs. So oxidation occurs at the anode, which then means that reduction would occur at the other electrode, and we call that electrode the cathode. Okay, so oxidation at the anode, a reduction at the cathode. Okay, so we have our galvanic cell, or voltaic cell that we use. That is a combination of each of these half cells. So electron then is going to flow from the anode, where oxidation is occurring, to the cathode, where reduction is occurring. And the reason there is because there is a difference in electrical potential energy between these electrodes. And if we were to connect these with a wire, we can actually measure that electrical potential by a voltmeter, for example. And we call that amount of voltage, we call it the cell potential, often abbreviated as E subscript cell, or sometimes it's called the electromotive force, which is often abbreviated as EMF, or the cell potential, or the cell voltage. All of these are used interchangeably to refer to that voltage that can be measured when we connect these two half cells with each other. Now, in order for this to work properly, in order for these half cells to generate that voltage, we also need to connect these half cells. So this here is showing you if we were to connect those same two situations, we have our copper here, and our copper sulfate, CuSO4 solution. We have our zinc electrode and a zinc sulfate solution. Right, if we were to connect these to an external wire, this is our voltmeter that we have. We'll see that that voltage ends up being 1.10 volt. What you will also notice here is that there's this thing called a salt bridge that is in contact with both of these solutions. And what this allows is it allows ions to flow to complete that electrical circuit. So electrons to flow through the external wire, right? We still need to ensure that the cations and the anions that are in those solutions that we're using are able to flow from one half cell to the other. Okay, if we didn't have that salt bridge, which is just simply like a U tube or an inverted U tube, for example, a wire tube with some sort of a gel or something in there that has an inert unreactive electrolyte solution like KCl. So for example, potassium chloride, for example, is in that salt bridge, or sometimes ammonium nitrate. If you didn't have that in there, there'd be a buildup of negative charge in the cathode compartment, and that would quickly prevent that cell from operating, right? So the salt bridge is there to perform a very important function, which is to allow the cations and the anions to flow from one half cell to the other. So the salt bridge is critical for this setup to actually work. So we have our galvanic cell that can be made by combining two half cells. We have in each half cell oxidation and reduction occurring in each of them. Oxidations happens at the anode, reduction happens at the cathode. So that electromotive force, that EMF, that cell potential, or that cell voltage that cell potential that we measure, right? That voltage itself depends on several things. Okay, it's going to depend on the electrodes, obviously, the anode and the cathode, for example. It depends on the ions that we have in solution, but it also depends on the temperature. Okay, and it also depends on the concentration of those ions that we have. So we can represent the notation that we use to represent our galvanic or our voltaic cell is as follows. So in the case of our cell that we have by combining these two half cells, we have the notation as follows. So we have our zinc solid that's shown here, and then we have this solid line. So that vertical line that represents a phase boundary, and it separates one phase, like a solid phase, from an aqueous phase, for example. And then to the right of it, we have that, in this case, the aqueous zinc 2+ ion. So you have a solid on the left side of this single line. We have a aqueous species on the other side of it. Then we have this double line here, and this double line is meant to represent that salt bridge. And then on the other side, we have this something similar happening at the other electrode. So on the right side of it, we have our cathode, which is where reduction happens. Okay, on the left side, we have the anode where oxidation happens. And it kind of shows us what's going on here. So the zinc becomes zinc 2+. That's oxidation, obviously. Here, the copper 2+ becomes copper metal. That's reduction. Again, here, we have the single line that separates one phase, the aqueous phase, from the solid phase on the side. Right, so we have our anode, our oxidation on the left side, the zinc electrode, metals separating the aqueous solution. Here we have our 1 molar. We typically represent the concentration. We have our salt bridge, and then we have the cathode reduction on the other side. In this case, the copper 2+. Again, 1 molar. And our phase boundary with the copper metal, the copper electrode on that side. That's your typical cell notation that we have that we're going to be seeing from this point onwards. So one more thing that we want to keep in mind, because we can, again, set up these half cells. We can connect them through an external wire through some sort of a voltmeter. So we can measure the potential or the voltage for that cell that we've just constructed. And we want to keep in mind what that voltage, what that potential actually means, right? So the volt itself, so voltage is a derived quantity, okay, and that is It's a derived SI unit. We get it from, so 1 volt is equivalent to 1 joule of energy divided by a charge, the coulomb, in this case. So a volt is joules per coulomb. So we want to keep that in mind. This is going to be very important when we start looking at some of the calculations in the subsequent section. So the voltmeter that we use to run those electrons through, that measures the cell potential, the EMF, the cell voltage when we connect these two half cells, a reduction and an oxidation to each other.